Hi everyone, my name is Rachel Chimuka, and my presentation is on carbon cycle feedbacks under positive and negative CO2 emissions. Before I proceed, I'd like to thank the organizers of the AGU Fall Meeting for the opportunity to present my research. So I'll start off with a brief background on carbon cycle feedbacks under positive and negative CO2 emissions, and then I'll outline my research objective as well as the methodology, particularly the climate model and the model simulations I used. Then in my results section, I will discuss the differences between carbon cycle feedbacks under positive and negative CO2 emissions. And then I'll close off with a summary and an outlook into the next steps for this research. The Paris Agreement stipulated that warming should be limited to well below 2 degrees Celsius above pre-industrial levels, and that further efforts should be made to limit it to 1.5 degrees Celsius. Now, the image you see on the right there shows net CO2 emissions for a range of emission scenarios. And it is this RCP 2.6 emission scenarios that are consistent with our climate targets. And we can see that for RCP 2.6, we not only have to reduce our CO2 emissions, but reach a point of net negative global emissions, where we're taking out more CO2 from the atmosphere than we're putting in. Now, the land and ocean play a major role in regulating our anthropogenic CO2 emissions by absorbing approximately 50% of those emissions. And this absorption is governed by two main feedbacks. The first being the concentration carbon cycle feedback, in which an increase in atmospheric CO2 concentration increases the carbon uptake in the land and the oceans, decreasing that atmospheric CO2 concentration. The second feedback is the climate carbon cycle feedback, in which CO2-induced warming decreases carbon uptake in the oceans, causes outgassing on land, and then results in an increase in atmospheric CO2 concentration and further warming. Now, once we apply carbon dioxide removal, we see that the land and the ocean first take up only a fraction of the remaining CO2 in the atmosphere. And then once we reach global net negative emissions, when we're taking out more CO2 from the atmosphere than we're putting in, we see that the land and the ocean switch and become sources of carbon dioxide. And that means that we can expect the outgassing of CO2 from the land and the ocean to counteract our efforts at decreasing CO2 levels through negative emissions. Now, research has so far focused on carbon cycle feedbacks under positive CO2 emissions, and very little has been done on carbon cycle feedbacks under negative CO2 emissions. So my research objective is to investigate to what extent carbon cycle feedbacks under positive CO2 emissions differ from those under negative CO2 emissions, with a focus on land processes. To do this, I used an Earth System model of intermediate complexity. That's the University of Victoria Earth System Climate Model, version 2.10. Now, this version of the model includes a 2D energy moisture balance atmospheric model, which is coupled to a 3D ocean general circulation model, which includes both organic and inorganic carbon cycle models. Coupled to the ocean model is a dynamic thermodynamic sea ice model that simulates sea ice dynamics, as well as the heat exchange between the sea ice and its environment. And then on land, there's a land surface model that includes a permafrost carbon model that simulates carbon dioxide emissions due to permafrost carbon decay. And then coupled again to that land surface model is a vegetation model that simulates or that represents 5 different plant functional types. So to quantify the carbon cycle feedbacks, I used a carbon cycle feedback framework from Friedlingstein et al. That uses integrated flux-based feedback parameters beta and gamma. Now, in this feedback framework, simulations are run in 3 different modes, the first being the fully coupled mode, in which the land and the ocean respond to changes in CO2 concentration and climate. And so the change in land carbon, for example, would be equal to the sensitivity of land carbon to changes in CO2 multiplied by that change in CO2 plus the sensitivity of land carbon to changes in temperature multiplied by that change in temperature. Then the same can be done for the ocean here. In the next mode, that's the biogeochemically coupled mode, the land and the ocean respond to changes in CO2 concentration only. And so this mode represents the concentration carbon feedback, and changes in land and ocean carbon can be determined from the equations on the right. In the next mode, the radiatively coupled mode, the land and the ocean respond to changes in climate only. And so this mode quantifies the climate carbon feedback, and the changes in land and ocean carbon can be determined from the equations on the right as well. Now moving on to the model simulations. So first, I ran a one-time CO2 spin-up in which the model was spun up with year 1850 pre-industrial CO2 concentration of about 280 parts per million. Then following from that spin-up, I ran a transient simulation in which CO2 was ramped up from pre-industrial to 4 times CO2 and then ramped down back to pre-industrial levels where it was held constant. So in this simulation here, the positive emissions phase here represents the response to the positive emissions alone, and that's because the positive emissions were applied from an equilibrium state. However, in this ramp down phase here, the negative emissions phase, the response here is not only due to the negative emissions, but also due to the prior positive emissions, because the negative emissions here were applied from a transient state. Now, this simulation was run in the 3 modes mentioned earlier. All other radiative forcings were held at pre-industrial levels, and then the permafrost carbon decay was switched off. In addition to the transient simulation, I also ran a zero emission simulation following from the same one-time CO2 spin-up and the same ramp-up phase as shown in the transient simulation. In the zero emissions phase here, the CO2 emissions were halted, and then CO2 was allowed to evolve. So the zero emissions phase here represents the response to the prior positive emissions alone, because those positive emissions were applied from an equilibrium state as well. In terms of simulation modes, radiative forcings, and permafrost carbon decay settings, all of those were kept the same as in the transient simulations. Now moving on to my results section, I'll start off with the land carbon cycle feedbacks under positive CO2 emissions. And the figures you see on the left there show the change in land carbon uptake against the change in atmospheric CO2 concentration and the surface temperature change. Figure A here is taken from the biogeochemically coupled simulation, where the land and the ocean only respond to changes in CO2, whilst figure B is taken from the radiatively coupled simulation, in which the land and the ocean respond to changes in climate. In figure A here, we see that as atmospheric CO2 concentration increases, the land takes up carbon, and that's due to the CO2 fertilization effect. Whereas figure B shows that with warming, the land loses carbon due to increased rates of plant maintenance respiration and soil respiration under higher temperatures. Now the figure A you see here is the same figure A shown before, but this time I've added the dot dash line here that represents the negative emissions phase. And we see that in the negative emissions phase, as CO2 concentration decreases, the land continues to take up carbon for a few decades before it switches into a source. And because the changes in land carbon are determined by the balance between net primary productivity, that's NPP, and soil respiration, we can use the figure on the right here to determine the reasons for the changes we see in figure A. So we can see that in the negative emissions phase, the NPP decreases due to the weakened CO2 fertilization effect, whereas soil respiration declines more slowly due to the decreasing soil carbon. Now the figure B you see here is the same figure B shown earlier, but this time the dot dash line has been added to represent the negative emissions phase. And we see that with cooling, the land continues to lose carbon for a few decades before it switches into a sink. And again, the reasons for those changes can be found in the balance between NPP and soil respiration. And we see here that NPP increases, and that's due to increasing gross primary productivity and declining plant respiration rates. And then later, NPP starts to decrease, possibly due to the negative effects of lower temperatures on vegetation in the high latitudes. In terms of soil respiration, we see that it decreases due to declining surface temperature. Now the table you see here shows feedback parameters at 4 times CO2, that's at the peak of the ramp up and ramp down transient simulation. And we see here the feedback parameters for this study using version 2.10 of the model and a previous study using version 2.9 of the model. And then these are compared to the feedback parameters taken from CMIP 6. And what we see is for beta on land, the feedback parameters in versions 2.9 and 2.10 are well within the range, whereas for gamma on land, the feedback parameter for this study is outside that range, and that may possibly be because there's so much more soil carbon within this version of the model, since it also includes permafrost carbon. So the figure you see here is a summary figure with figures A and B are the same as what you've seen before, and I've added figures C and D for those interested in the ocean response. And for the ocean, we see that in figure C, in the negative emissions phase, as CO2 concentration decreases, the ocean continues to take up carbon for several decades before it starts to lose that carbon. Whereas in figure D, with cooling, in the negative emissions phase, we see that the ocean continues to lose carbon and does not turn into a sink of carbon within this time scale. So generally what we see is that there are differences in the behavior of carbon cycle feedbacks under positive and negative CO2 emissions, but these differences are likely largely due to climate system inertia, because in the negative emissions phase, the response is not only due to the negative emissions, but also due to the prior positive emissions. So in order to isolate the response to the negative emissions alone, we could use a zero emissions simulation, an example of which I have shown here. So this simulation here is a fully coupled zero emission simulation, which means that here the land and the ocean respond to both changes in CO2 and temperature. And the solid line here represents the positive emissions phase, which is similar to in the transient simulations shown earlier, whereas the dotted line is the zero emissions phase. And we see that in the zero emissions phase in figure A, the atmospheric CO2 concentration decreases slowly, and that is due to uptake from the land and the ocean, but mainly due to the ocean uptake. In figure B, we see that the surface temperature continues to increase, and that is mainly due to ocean thermal inertia, which keeps temperatures increasing despite the decrease in CO2 concentration. In figure C, we see that the land continues to take up carbon for about a year before it starts to lose it, whereas in figure D, we see that the ocean continues to take up carbon for more than a century, which just shows that there is larger climate system inertia in the ocean than there is in the land. So here are my conclusions. Under positive CO2 emissions, the land takes up carbon due to the concentration carbon feedback and then loses it due to the climate carbon feedback. As the CO2 concentration decreases under the negative CO2 emission phase, we see that the land continues to take up carbon for a few decades before it switches into a source. But with a decrease in surface temperature, we see that the land continues to lose carbon for a few decades before it switches into a sink. The differences we've seen in the behavior of carbon cycle feedbacks under positive and negative CO2 emissions are likely largely due to climate system inertia, because the response in the negative emissions phase is not only due to the negative emissions, but also due to the positive emissions. And so to isolate the response to the negative CO2 emissions alone, a zero emission simulation could be used.